Okay, let's start. Any question?
Is it going to be just covering material after the first?
No, it's just you know the knowledge points after the midterm.
Okay.
So we will not have the stuff before midterm. I think the major part will be the five-stage pipeline and the average memory access latency. Since I released that question. I released the question 6 in homework 4. So I included this one in this review, but we will not include this one in the final examination. But the question like Q5 will be similar question to Q5 will be included in the final examination. So the first 4 questions in this review are related to the 5-stage pipeline, and I will just ask the details, the functions of these components. You can just check in the review slides. And then we will have some average memory access latency calculation. And during these calculations, of course, we will have a cache and a DRAM. And we will also cover some basic knowledge of the DRAM. For example, the open page policy, the closed page policy. And then the cache. At least you need to understand the difference and semi-associative cache. I think that's all. So 5-stage pipeline. Average memory access latency, including the cache, including the DRAM, and then the DRAM destructive read, open page policy, closed page policy, and then the cache, fully associated cache, direct map cache, and a set associative cache. That's all. Any question on this review? Yes.
We do any calculations around latency? So we talked about that in class. We didn't.
What do you mean by DRAM latency?
Like we talked about some sources of DRAM latency, like
Activation,
yeah,
column sensing. No, we will not have that. But again, that part is related to the open policy. Right. You need to understand which type of application favor which type of policy and why. Then I will just, I will briefly introduce the points I feel like they are important. And then if you have any questions, you can interrupt me. So for the 5-stage pipeline, we will just ask some details in each stage. For example, this is the instruction fetch stage. We have two important components. One is the adder. The other one is the mask. The adder is used to compute the memory. The instruction address. Right. So this one is compute the effective instruction address. What's the next instruction? And you also have a branch here. So another input of this mask is the branch address. So by this mask, you can decide whether you do the jump or run the application, run the code sequentially. And compute the consecutively executing instruction address. We add a offset on the so for the sequentially executing the address, the offset can be 8 or 4, depends on your CPU. If it's a 64-bit CPU, this is 8. Why? Because log 2, log 64 is 8. If you have a 32-bit machine, then it's a 4. Otherwise, you can just add offset. This is defined by branch. So that's the branch address. This is the instruction decoding stage. And this is the register file. You can read the register AEM from this file. For example, if you compute something like this, during the instruction decoding, you can read the value of A and B from the register file. And then these two lines indicate that you do the write back. When you do the write back, So the destination register is the C. This one is the and the value of it, for example, the result of the C is the 10, and this is the data. So the name of register C is the destination register, and the value of the C is the data. So this is an execution state. This mask is used to select the second register of the immediate data. So sometimes you can have an instruction like this. You may also have some other instruction like this. So this is the immediate data, and this is the register B. So this mask is used to distinguish these two types of instructions. And then the read back stage. For this mask, it select the data. The data means sometimes you have these instructions, each computed by the ALU, by the execution stage. Sometimes you have this memory visit instructions. You load something to this register C. So this mask is used to select the ALU results, all the loaded data from memory. The data you loaded from memory. And the second mask here is used to generate the destination register name and the write enable signal. The second one is used to generate so again, we introduced the 5-stage pipeline. Here we only cover 4 of them. There's no memory visit part. Besides these details, you need to understand why do we need this pipeline design. So remember that laundry example. Assume that each stage costs you 10 nanoseconds. You have 5 stages pipeline. Each stage costs you 10 nanoseconds. If you do not have a pipeline design, then when you run this pipeline, 5-stage pipeline sequentially, have no overlap. Each stage costs you 10 nanoseconds. So totally, you will need 50 nanosecond latency for the whole thing. So if this is your total latency, this is your frequency. So this is your, you can only operate at 20 megahertz. So again, if you have the pipeline design, then this is your frequency, because now you can overlap everything. You can form a pipeline kernel. If you don't understand what I'm talking about, check that laundry example. After you have the pipeline, this is your frequency. Then you can run at this frequency. So by the pipeline design, we can break a large task into multiple pieces, into multiple stages. And then the frequency will be decided by the latency for each stage. And then you can run at a higher frequency. So that's all for the five-stage part, five-stage pipeline part. And then we have the average. Here we have three levels of cache. And different caches, different level caches have different heat rate. So I leave the heat rate here in this column. And then we have access latency here. Besides the three-level cache, we also have a memory. Then the question is, what's the average memory access latency? Yes.
Is there a specific slider area for the relation between the equation?
It's really difficult to summarize it into an equation, but if you can understand this question, I believe you should be okay. And of course, we have those similar questions in the DRAM slide or the cache slide. So how to compute the average memory acceleration? This is the access latency for the level 1 cache, and this is the heat rate. So for all your memory access, 80% will be served by L1 cache. Then you also have 20% misses. In this 20%, 60% will be served. In the L2. And then 20 cycle is the L2 access latency. And then the other 40% in this 20% will go to the L3 and the DRAM. So in this 40%, 40% will hit in the L3. The other 60 will go to the DRAM. So you can see that the first line will go to L1, and then the second line will go to L2. The third line will go to L3, and the last line will go to DRAM. And then you just need to add them together. So if you are looking for some equations, I believe this figure can summarize that equations, because you have three levels of cache in this example, and also the DRAM. So I think this question is the most complex example you can have for such type of design. Again, I will repeat again. So for your all memory access, 80% will be served by the L1 cache. And then you can use one minus this 80%. Result is 20%. For this 20%, 60% will be served by the L2 cache. And then you can use 1 minus 40, 1 minus 60, which the result is 40. And this 40% will be served by L3 and DRAM. So in this 40% will be served by L3. And then the other 60 will be served by the DRAM. Question? Yes.
What's the unit on that? Is it like nanoseconds?
It's a cycle, just cycle. Since there's no frequency, you don't need to worry about the unit. You can just write the cycle. You can also write the cycle. So we will not have a question 6, some question like 6. But again, you need to understand the difference between the direct mapped cache, fully associated cache, and the set associated cache. So for the direct mapped cache, basically you just do a mode operation. Assume that you only have 4 frames in your cache. So this is the physical SRAM you have, and you can use them to build your L1 cache, your direct mapped cache. So basically, you only have 4 frames. So based on this picture, you have a block outside. Block outside decides the size of each block, because you have 6 bits here. Then the block size is 64 byte. Because in the memory, everything is a byte addressable. Since you allocate 6 bits here, then the block size is 64 bytes. So this means each frame here is 64 bytes. Again, you have 4 frames here, so-called frames. So how to index them? You can index them by the index. In this example, you have you have 9 bits. You have 9 bits here. So this 9 bits can index how many frames? 512 bits, 512 frames here. So if we exactly follow this bits allocation, then basically in our cache, we will have this much frames here. But I would like to simplify this example. I just have a four frames here. So if I have 4 frames here, I just need 2 bits here. So which is the bit 6 and the bit 7. I don't need this much index, but you need to understand what's the index. The index indicates how many frames you have in the development cache. And the block offset indicates the size of each block. And then I will give you one example how to use this direct mapped cache. When I issue a request with this address, how can you look up that cache? You just do a move. And the result will be 0. Then you will go to this frame to do the lookup. Because this is direct map cache, it's only possible for this address to be stored in this entry. Why? Because this is a mode operation. The mode operation decide you can only use that particular frame. If I send you another address, 100, so this is a decimal address, not a binary address. If I send you another address here, you also do a mode, and the result is still 0. You will also go to this entry, the same entry. This means that even I didn't use the other 3, these 2 requests will compete for the same entry. Which means that potentially you can have a lot of conflicts. And you know, the tag here is some record, which can help you to distinguish these 2. So you can see that we first, allocate the blocks offside because each block is 64 bytes, so we allocate 6 bits here. And then the index here is decided by how many frames we have in the cache. And it's also decided by your cache itself. Then all the other bits, because you have a 64-bit address, all the other bits are tags. You can use all the other bits as tag. And the tag can help you to distinguish these 2 addresses. The lookup operation is very simple. You just do a mode operation. And then you go to that particular entry. And it's only, there is only one possible location for each address in this so-called direct mapped cache. Any questions? Yes.
Do the mod operation based on the number of blocks you have? So,
Yes, because this 4 is exactly this 4.
okay, that's what.
So if you have 8 frames here, then you just mod 8. So if I change this address, then it will go to this entry, the second entry. So the advantage of direct map cache is that the lookup is very fast because you only need to do a mode operation. Typically, this value, the frame number is a 2 to n value. Then you can use just shift to do the mode operation. The lookup is very fast. But the disadvantage is that even I have a very large cache, I have a lot of entries here, a lot of frames here. Potentially, we will have a lot of counting because many entries here will be mapped into the same frame. And then we will have the fully associated cache. Fully associated cache means when I give you a address, this address can possibly be stored in all the entries. Not only just this frame, but all the frames here. How to do the lookup? You need to compare them one by one. So and then if I give you another entry here, this one can also be stored in any entry, possibly in any frame of this cache. You also need to compare the tag one by one to find that one. So the fully associated cache has a higher hit rate because it's very flexible. You have more options to store your data. But again, when you do that lookup, you need to compare them one by one. There are 4 possibilities here. So remember that direct map cache, there is only one possibility. Here we have 4 possibilities. So the advantage is a high hit rate because you can have more position more frame to store the request, but you need to do the lookup, do the comparison more to find that value. So that's the fully associated cache. Yes.
Can you explain a little bit about the bottom of
No. This slide is an n-way set associated cache. I'm just talking about fully associated cache. And then we will move to the n-way set associated cache. So again, you can see the disadvantage and the advantage of a fully associated cache and the direct map cache. And then someone just combine them together to have both the advantage of both. So this is one. That's the set associated cache. This figure, it actually shows the two-way set associated cache. So this is one way. This is one set. So the concept of set is also the mode concept. When I give you a address, you just do a mode. Assume that we have a 4 set. After we do the mode, the result is still 0. So you go to the set 0, like this one. And the set 0 also indicates this line and this line. This is the set 0 in this two-way set. The set concept is just a mode concept. You do a mode and then you can find your set. This is your set, which is the set 0. Because the result here is the mode result. So this is the same as the direct map cache, but Difference is that in this set, you have you have two entries. And this two entry is so-called fully associated. Once your address is mapped into the set 0, you have two options to store the data. You can either store it here or here. Inside each set is a fully associated. So in this way, you combine the direct map. So for the set, first you decide the set number. How can you decide the set number? You just do a mode operation, which is the same as the direct map hash. After you have your set number, you go to that set, and then you have n way. In this example, it's 2 way. Then you have 2 entries as the fully associated hash. Your data can be stored in any of them. So for the comparison, after you do the mode operation, you just do 2 comparisons in this example. For n way, it's just n comparison. We may not, have such details in the final examination. But if I give you some question like this, I give you a cache configuration. For example, you have 4 frames here, and it's a direct map cache. And then I give you a sequence of address. Can you compute which address will be hit in the cache? Which address will analyzes the hit or miss cycle, request by request, cycle by cycle in this cache? Yes.
So if you were to give this, probably won't, but if you were to give this the same question and not use direct map hash, you use the set associated hash, that's fine. Set. And then
Yes.
like the 2 ways.
Yes. Exactly. And then the DRAM. So the DRAM use chunks to represent 1 and 0 if you have chunks 1, otherwise it's 0. So the read operation always starts from a chunk bitmap to VDD. So you can see that the starting point is always 0.5 VDD. And then you can use your bitmap to sense the content. If your cell has some chunks, then the chunks will flow from the cell to the bitline. So the bitline voltage will increase. Otherwise, the chunk will flow from the bitline to the cell, and the bitline voltage will decrease. But the voltage in the cell will be eventually 0.5 VDD. So 0.5 VDD is not 1 or 0, so the content in the cell will be distracted. So this is so-called a destructive read. So you have a memory line here, and then you do the read operation. Different color indicate different values. Blue is 1, red is 0. After you do the read operation, the content, the data will be stored in the Cypher paper. And then your cell has no more data because the data has been destroyed. So you can see that the Cypher paper and the robot are actually targeted concatenated together. So after the read operation, you have some cases like this. The data is stored in sense amplifier and the row buffer. But your memory cell has no more data because the content are just destroyed. In this case, you have at this moment, you have two options. Two options are the closed page policy and the open page policy. So if you just keep everything like this and waiting for another read operation, this is an open policy because you just read everything in that box. This is an open page. So if the next access, next request, asking some data in this row buffer, then you make the right decision. You can just return to the request. You don't have to do anything. You just return the data. That's all. So the open page policy is friendly to applications that have a very strong spatial locality. If you sequentially access a portion of the memory, you should adopt this open page policy. But if your next request asks for another row, then you have to restore the value to the memory first, and then open another row. So in this case, the open page policy is slow, and you should adopt the closed page policy. In the closed page policy, after each read operation, you just do the write back, you just do the restore. So at least the difference between two policies as this table. N+1 indicate you just sequentially read your data. N+R indicate you just random read your data. R indicate a random number. So for the open page policy, in this case, you just return the data. You don't have to do anything extra things. You just return the data. It's the fastest operation you can do. If it's random, you just close the row, restore. You just restore. And active another. Activate another. You do two operations. So if you adopt a closed page policy, because you have already done the restore, you just activate one row. Activate one row. Again, you also activate one row. So the closed page policy basically do the same thing for these two cases. Any question on this one? So this question is also about question is also about the average memory accessibility. The difference is we have this memory level parity. For the memory level parity, we just divide this one. We have different lines here, and you just divide this memory level parity at the end of that line. For example, memory level parity is 8 for the memory for the DRAM. In this item, you just divide it by 8. Any question on this one? And the last one is also the cache. I explained the cache in previous slide. Bring your calculator if you need for the final examination. The final examination, you can also print out the the policy are the same as the midterm. If you have any question, you can ask me now. Otherwise, we can stop. Thank you.
Let's make file where you specify the type of replacement, and it's just going to use a macro. But, I don't know. I'm doing a whole class for the binary search tree, and I didn't know specific type of implementation. I don't know how it's going.
Which policy?
So for like my replacement, I have each policy is just separate here. But then for the pseudo LRU, the PLRU, the binary trees, it's as a class. They're okay, just have it all macro.
Okay, that works.
Okay. And then if I end up, I mean, I don't know if I'll have time, but if I do end up doing like the pre-fetch, like, will that just end up like that's okay if I edit the main method?
I think it's okay.
Okay, cool. I'll try to like have a readme that explains what's what, because like I don't think that this is obvious how to use it.
So different policy. For example, the pseudo LRU can be implemented by multiple schemes.
Right.
I don't think you need to implement all the schemes and then say which one is better. So if you can see the improvement achieved by the pseudo LRU over the random, over the not most recently used.
Right.
I believe that should be very good.
Okay. Yeah, because I think I only got this function enabled right now, but if I run it. Oops. There we go. Let's do And I'm gonna use 0.5 lowest level. It's like those are about the same.
Again, not only for this particular benchmark, you can try.
Yeah, I've got all of them. I just haven't commented that right now.
Yes, yes.
It's then the screen gets kind of hard to interpret. Okay, cool. So then I'll just keep doing it like that because all I have left to do is the PLRU.
Yes.
But okay, cool. And then I get my tablet. So even though it's not going to be on the final, I do want to look at